Welcome to Study Loop.
In this problem, we're going to talk about the Schrodinger equation. So we need to remember that the time-independent Schrodinger equation is the following. So it's minus h bar squared over 2m times the second partial derivative of the wave function plus the potential energy function times the wave function. And this is equal to the energy times the wave function. So this is the differential equation called Schrodinger equation. Um, Okay, and the wave function is a function that describes the system we're working with. Also, besides the differential equation itself, we also need the uh, boundary conditions. So we have the conditions that the function, the wave function, must be continuous at all points, and that at points where the potential energy is not infinite, the derivative must also be continuous. Continuous at u different from infinity. Okay, so now we are in a position to move on to our exercise. So what we have is potential energy that is equal to the following. It's infinite for x smaller than 0. It is equal to 0 for x between 0 and L, and it's equal to u0 for x greater than L. Okay, greater or equal than L. And in question A, we have to solve the Schrodinger equation and use that the wave function is continuous at the origin, meaning that the wave function must be equal to 0 at the origin, since the potential energy is equal to infinite at this point, to find what is the form of the solution of the wave, uh, the wave function at the region 0 smaller than x smaller than L. Okay, so notice that in this region u is equal to 0, so h minus h bar squared over 2m times the second derivative of the wave function is equal to e times the wave function because u is equal to 0. So the second derivative of the wave function is equal to minus 2me divided by h bar squared times phi. E is positive because it's the kinetic energy of the particle, so this term here is negative. And I'm going to define k to be equal to 2, to the square root of 2me over h bar squared. So we obtain that d2 phi dx2 is equal to minus k squared phi. And the solution to this equation is that phi is equal to a times the sine of kx plus b times the cosine of kx. Okay, but we have to impose that phi of 0 be equal to 0. Now, phi of 0 is a times the sine of 0 plus b times the cosine of 0. Now, the sine of 0 is 0, so the first term vanishes. We get that 0 is equal to b since the cosine of 0 is 1. So since b is equal to 0, phi must be equal to a times the sine of kx. So this is the equation, the solution to question A, I'm sorry, where k is the square root of 2 and e over h bar. And in question B, we have to find what is the form of the wave function in the region where x is greater than L, given that the wave function must be finite when L tends to infinite. Okay, so the wave function cannot explode. It actually must go to zero. So more than just being finite, it has to vanish. So notice that at this region, we have that the potential energy, U of x, is equal to U0, and U0 is greater than the kinetic energy of the particle. Okay? So the Schrodinger equation is h bar squared over 2m times the second derivative of the wave function plus U0 times the wave function is equal to E times the wave function. So minus h bar squared over 2m d2 dx 2 phi is equal to E minus U0 phi. Sorry. So minus h bar squared over, I'm sorry, actually, let me do it like this. D2 dx2 of phi is equal to 2m u0 minus z divided by h bar squared times phi. And I'm going to write this equation as, notice that this whole term here is positive because u is greater than e, u0 is greater than e. I'm going to call it k prime. So k prime is equal to 2m u0 minus z divided by h bar squared, and then I'm going to take the square root of it all. So d squared dx squared phi is equal to k prime phi, and the solution is a times z to the minus k prime x plus, actually, let me not use a, I'm going to use c and d because I had already used a back in question A. Okay, so this is our equation, this is our solution. Now notice that for x going to infinity, we must have that phi vanishes. So this term may not be here because this term explodes as x goes to infinity. The other term, however, does not explode and goes to zero the as x goes to infinity. So d must be equal to zero. Phi, on the other hand, is c times z to the minus k prime x. So this is the form of the wave function. And then in question C, we have to impose that at the boundary between the second and third regions, that is at x equals L, the wave function must be continuous. So uh, phi of L plus is equal to phi of L minus, just as the derivative must also be continuous. Okay. Okay, so we can go on and solve this. We have that here I'm using L plus for the right side of the wave function. So basically the wave function for L plus is equal to C times E to the minus K prime times X. So X in this case is L. And phi of L minus is A times the sine of K times L. The derivative is minus K prime C e to the minus K prime L, and this is equal to K A times cosine of KL. And what we have to do, according to the exercise, is to show that K times the cotangent of KX, I'm sorry, of KL, is equal to minus k prime. Um, and in order to show that, I'm going to divide the two equations that I have here to obtain the c's cancel out, the exponentials do as well, so does the a. So we have minus 1 over k prime is equal to tangent of kl divided by k. So we have that k times the cotangent of kl is equal to minus k prime. I just inverted the equation. Um, so this is exactly what we wanted to show. And this concludes our exercise.